We're going to continue on where we're lecturing again with all the holidays and stuff that we got going on or had. I'm try to get back on pace a little bit here since we only have one lab scheduled for today. We'll see how that goes. I don't know. I think maybe the earthquake's a bad sign that maybe we shouldn't do that. I don't know. But here we go. We were talking about gases here, and we obviously just did the combined gas law, which, like I mentioned before, is really a good one to remember. As we talked about, you again can get from it pretty much all those other gas laws that you might need. Remember, pretty much all you have to do is just basically scratch out what's not given to you, whatever is held constant, and you'll pretty much be left with your gas law that you probably need in that case. Again, adding to that, obviously, our ideal gas law, that if, again, you use the ideal gas law, it is the most restricted, as we talked about, in terms of units. They have to be in those units that we talked about. Again, atmospheres for pressure, volume liters, moles should be moles, temperature should be Kelvin. And really, again, that is based off of R. And it has all of those units in it, which is why everybody else needs to be, again, in those same units. So everything that properly cancels out. So the next thing we're going to talk about is stoichiometry involving gases. So just like regular stoichiometry sort of problems, you can have a stoichiometry problem that involves gases, much like the experiment we did the other week or last week. The good news is it's really the same steps that you do for a stoichiometry problem. Nothing really changes. You still want to roll through those 4 steps, which is balance the equation. You want to convert to moles. You also always, even though it might be a gas sort of situation, you still want to make sure that it's not a limiting reagent problem. So if it is, you might have to do the limiting reagent step. Then we want to do our stoichiometry using the limiting reagent, mole to mole relationship. And our moles is some other unit. And the main difference here when you're doing stoichiometry involving gases is somewhere along the way, you're going to use a gas law pretty much, yeah? And it could be really in 2 spots usually. You may use a ideal gas law here. So you may use PV equals nRT. And I would say if you're using it up front, you most likely will be solving for N. So you may use the ideal gas law up front here to solve for N to get your moles. But I would say probably very commonly is you'll actually use like the ideal gas law at the end of the calculation there. And maybe you're looking for a volume, which is a very common sort of outcome type of calculation. So that's really the main difference. Everything else is exactly the same. You could still have a limiting reagent problem, or it may just be a basic stoichiometry problem. But somewhere along the way, either at both of those steps or one of those steps, you will use pretty much the ideal gas law and solve for whatever it's looking for. So instead of like normally we were looking for grams at the end, we may be like in the experiment looking for the volume you produced of the gas or something like that. Any questions on that there? Yeah. Yeah, I would say probably 99 times out of 100 is probably gonna be that. But you could use like in the experiment, you could use like the combined gas law. I would say either probably the combined gas law or the ideal gas law, but probably 99.9% of the time it's going to probably be a version of the ideal gas law. It's most likely what you're going to use. But you could use, for example, the combined gas law at the end or something like that. Yeah. Other questions? All right, so why don't we try one here? What is the volume of CO2 that's produced? Put an arrow too, that'd be helpful. At 37 degrees Celsius and 1 atmosphere, if you started with 5 grams of glucose are used up in this reaction. So some numbers will be helpful. Carbon 12.01, hydrogen 1.008, and oxygen 16. All right, so take a few moments. Again, follow those steps. Again, incorporate probably an ideal gas law in here somewhere along the way and see what you end up Okay, let's take a look. So obviously this is a stoichiometry problem. And I'm just going to rewrite a little bit higher so see everything here. So basically we have, we're looking for the volume, right? We're looking for the volume of CO2. We do have the pressure given to us, which is 1 atmosphere. We do have the temperature given to us, which is 37 degrees Celsius, I believe. Um, and the other piece of information we're given is we're starting with 5.6 grams of glucose. Obviously, CO2 is a gas, and I have a volume, a pressure, and a temperature. So again, we should think about the ideal gas law at some point. We will probably need to use it. We're going to be looking for a volume. I have a temperature, I have a pressure, and I have R. So really for the CO2, what I'm missing is the moles in order to actually use the ideal gas law. So the place where I could get to the moles of CO2 is going to be based on the other piece of information that was given to us, which is the grams of the glucose. So we could do really a stoichiometry problem here, just like normal. It's also not a limiting reagent problem because I only have information about one reactant, not both, right? So it's just a basic stoichiometry problem. So that means I want my equation balanced, which it is. I then want to convert what they gave me into moles. So 5.6 grams of our C6 H12O6. Once again, going to the periodic table here, adding everything together. That would be 6 of our 12.01 for the carbon, plus 12 of our 1.008 for our hydrogen, plus 6 of our 16 for the oxygens. And I believe that's going to get us here 208.8, I believe. And that should get us what we should use for our molar mass for our glucose. Double check, make sure. How about 180? Does that sound better? I know. Yeah, I didn't feel right to me when I was doing it. Let's try that again. How about 180.2? That seems better. Let's try that there. 180.2 grams per mole. All right, so we're going to use that as a conversion factor here. So I'll go 180.2 grams per mole of our C6H12O6. Going to give me 5.6 divided by the 180.2. Here again, I'm not going to round too much here, so 0.031077 moles of our C6H12O6. Remember that we're actually looking for moles of CO2 so that we can use the ideal gas law. So basically, actually, this is step number 2. We're going to do our step number 3, which is our stoichiometry. And from the equation, it is 1 mole of C6H12O6 gives us 6 moles of CO2. So that's what we will use. So we'll go 0.031077 moles of glucose. Doing our stoichiometry, which will get us our moles of our CO2, 1 mole glucose on the bottom, and 6 moles, bless you, of CO2 up on top. That's going to get us here times 6, looks like 0.1865 moles of CO2. So again, hope you can see kind of the same steps. The difference here is at the end, now we have everything that we need to go into the ideal gas law. So instead of using like molar mass here at the end, we're going to use the ideal gas law and we're going to solve for N. And N is going to be equal to PV over, why are we solving for N? We're not doing that, are we? I'll learn chemistry one of these days. It's okay. Let's try this again here. Let's try it again. We want the volume. So solving for volume would be a great move there. Volume would be nRT divided by P. All right. So N we just calculated 0.1865. Our R's are constant, which we always have, 0.08206 liters, atmosphere, Kelvin, mole. Our temperature, we do need to convert, so it's 37 plus 273.15. So 273.15 plus 37, 310.15 Kelvin. all divided by P, which in this case is 1 atmosphere, right? So our moles will cancel, our Kelvin will cancel, our atmospheres will cancel. We are going to be left with liters as our units in this case. I'll try to get the right number this time. Let me see here. All right, so let's see here. All right. So we're going to go 0.1865 times 0.08206 times 310.15, and we'll go 4.75 liters of CO2 would be produced in this case. By the way, since that is a product that would be produced, that is also a theoretical yield, right? So that is a theoretical yield in this case. Question on those steps. So basically same steps, just using the ideal gas law somewhere along the way. Try to use the right numbers would be good too, I suppose. Yeah. Any questions on those? All right, let's try a couple more here. All right, consider this reaction here. What is the volume of hydrogen gas at 27 degrees and 1.25 atmospheres that's required to react with 5.65 grams of phosphorus? Phosphorus is 3097. Okay, let's take a look. So once again, here we're looking for a volume of hydrogen gas, which is here. So we're looking for a volume. And again, we got some sort of useful gas information, if you will. We got a temperature that's 27 degrees Celsius. We also have a pressure that is 1.25 atmospheres. We always have R, since we're probably going to use the ideal gas law, 0.08206 liters atmosphere Kelvin mole. And again, if you kind of think about the ideal gas law, just like we had previously in that last problem, we really do have everything we need except for moles. And again, we're looking for volume. So once again here, we're going to use stoichiometry to get the moles of our gas that we're interested in, and then we could use our ideal gas law. So we have our equation, it's balanced. The other piece of information that we need to do and convert to moles is our phosphorus. So we're going to take our 5.65 grams of P4. We're basically going to times this by 4 to get the molar mass, right? So 3097 times 4. That will give us a molar mass, but I didn't screw it up this time, of 123.9 grams per mole of P4. By the way, that will cancel out our grams of P4 and give us our moles of P4. We then can really do the stoichiometry part in this case. And in this case, it is between these two guys. You could get an answer at this point if you wanted to, or you could continue on with the calculation. So I'm just going to continue on with the calculation here. I want to get rid of the phosphorus. So from the equation, 1 mole P4 gives me 6 moles of H2. So again, basically step number 2 in stoichiometry, step number 3 here in stoichiometry. So 5.65 divided by 123.9, then multiplied by 6, going to give us 0.2736 moles of H2. That again was sort of the missing thing that we needed. Once again here, we're not going to use molar mass on the back end. We're going to use our ideal gas law, which, as I mentioned earlier, is very, very common. So we're going to go with our volume to solve for, nRT divided by P. We do have to still do a conversion. And in this case, it looks like it is just the temperature, as our pressure is already in atmosphere. So that's good to go. So we'll do our 273.15 plus our 27. And that's going to get us 300.15 Kelvin. So popping those numbers in, we'll go 0.2736 moles. our gas constant, which we always have, our temperature converted to Kelvin, always in gas laws, all divided by our pressure, which in this case, 1.25 atmospheres. Atmospheres are going to cancel, moles canceling, Kelvin canceling, leaving us liters again, which is good since that is a volume. And in this case, we will end up with looks like a 5.39 liters of H2 in this case. This is not a yield because this is a reactant. So this is not like a yield or anything like this. So that's not a theoretical yield. That is if you wanted to do this reaction with that 5 point, whatever it was, 5.65 grams of phosphorus, you technically would have to put in there 5.39 liters of hydrogen to do this reaction and produce product. Question on that there? Because it's not a product. So a yield is always on the product. It's always a product, basically. So it has to be a product for it to be a yield. Yep. Other questions? It is technically what we just calculated is how much of the hydrogen gas you would need to throw in there to react with that 5.65 grams of phosphorus. Basically to use it all up, basically, in that sense. Yeah. Other questions? So if we were seeing a pattern here, so let's take a look at one more here, which is not that one. That's the one we just did. Let's take a look at this one, which is similar to what you, exactly similar to what you did there in the lab. So let's give it a go. Magnesium reacts with hydrochloric acid, as you saw, produce some hydrogen gas. We want to know what is the volume hydrogen gas produced at STP if you started with 5 grams of magnesium and you reacted it with excess amounts of HCl. So magnesium 2431. Okay, so let's take a look. So it's pretty similar to calculation did earlier. Um, Here we're looking for the volume of H2 gas at STP. Remember that when you are given STP, it does basically represent two values. That means the temperature should be 273.15 Kelvin and the pressure should be 1 atmosphere. And that means we basically have a P, a V, and a T. Again, we always have R available to us, 0.08206 liters atmosphere Kelvin mole. So once again here, we can use our ideal gas law like we did previously, as essentially we have all this information except for obviously again here the moles to allow us to use it. So we could do our stoichiometry like we did previously. We have an equation, it's balanced. We then want to convert it to moles. So 5 grams of magnesium using the molar mass from the periodic table, 2431 grams per mole of magnesium. Again, if I stop the calculation right at this point, I'm in moles of magnesium. I do need to get to the moles of my gas. And from the equation, we could see it's a 1-to-1 relationship. So I'm just going to continue on with the calculation here. 1 mole magnesium on the bottom, so it cancels. 1 mole of hydrogen gas up on top, they cancel. And that gives me the moles of hydrogen, which in this case is 5 divided by 2431. And that's going to give me 0.2057 moles of hydrogen in this case. First off, any questions on that there? At this point, I now really do have everything I could use to go into the ideal gas law. Here again, we will be solving for volume, which is nRT divided by P. Our N being our 0.2057 moles of hydrogen, 0.08206, our R constant here, and our 273.15 Kelvin, which is our STP, and our 1 atmosphere on the bottom. Moles are going to cancel, Kelvin going to cancel, atmosphere is going to cancel. Once again, leaving us liters at this point. And if we put all that in there, 0.2057 times 0.08206 times 273.15, going to give us 4.61 liters of H2 in this case. First off, question on the calculation. Would this be a yield? This actually would be a yield because it is a product. So this would be your theoretical yield here of H2. Again, it's a product, how much you should produce based on the equation. First off, any questions on that there?
What do you mean by excess?
It just basically tells you whenever you see in like a stoichiometry problem like excess of this, it reacted with excess of this. What they're basically telling you is it's not a limiting reagent problem. Whatever number they gave you is a limiting reagent, so you don't have to worry about it. Yeah. So that's why they say sometimes you reacted this much of this with excess amount of this. What they're basically telling you is whichever one they gave you the number for is actually the limiting reagent. So they kind of did the calculation for you, that part of it, and you don't have to worry about trying to figure it out. Now, if they said that, for example, in this case, that you took 5 grams of magnesium and reacted it with 20 grams of HCl, then it is a limiting reagent problem. You would have to figure that out first before you continue on. But anytime you see that in a stoichiometry problem, it just says like you reacted this amount with excess. It basically is just a basic stoichiometry problem. Whatever the number is, it's the limiting reagent. In that case, yeah. Other questions? Could I have solved this a different way? The answer is yes, because I am at STP, and I know that at STP, right, as we talked about earlier, 1 mole of any gas equals 22.414 liters, which means I could have just took this number, 0.2057 moles of H2, use that conversion, 1 mole of H2 would equal 22.414 liters. The moles would cancel. You'll get that number. So this is a situation, like I said earlier, that if you recognize it is at STP and you're looking for a volume here, you could have used that relationship without using the ideal gas law. But as you can clearly see, if you use the ideal gas law, you're okay. It's okay. So you don't have to use that. But remember, again, you should only use that if we're at these conditions. So again, if you're not at these conditions, you definitely should never use the bottom one, in that situation. Yeah. Question on that there? Yeah.
Understand like when it's a theoretical yield and when it's not.
Yeah.
Like,
Yeah. So it's really simple in the sense that all you have to think about is whatever you just solve for, is it a product or not? And if it is a product, then that is technically a yield, because that's basically what it means. That arrow means, if you were to say it in words, is you took magnesium and you reacted with HCl to yield those two things. So yields are always products. So if you ever calculate in a problem based on how much reactants you're starting with, how much product that you produce, that product would be your theoretical yield. Yeah. So if you calculate something in stoichiometry that you end up calculating how much reactants you got, that would be just a reactant. It's not a yield because it's a reactant. Yeah. Other questions? All right. Questions on solution stoichiometry? Let's try one more. Why not? Huh? Calcium carbonate reacts with hydrochloric acid to produce carbon dioxide gas. If you took 35.3 grams of calcium carbonate and reacted it with 21.6 grams of hydrochloric acid, how many liters of carbon dioxide would you produce at 745 millimeters of mercury and 23? So this would be a good practice of everything. That's highlighting, which is not good. Let's try that again here. All right, so why don't you give it a try? We'll put some numbers up here that'll be helpful. So calcium is 4008. Probably carbon there, 12.01. Oxygen 16. What else we got there? Calcium carbonate. Hydrogen 1.008. And chlorine 3545. There you go. I think that's everybody, hopefully. All right. So in this case, you got nothing. So you better start with an equation, I would think would be a good thing. and then follow the steps and see what you need to do. Okay, let's take a look, see how you're doing. So on this one, we're not given much, so we do actually need to start with the equation for old time's sake, right? So we're going to start with our calcium carbonate, which is CaCO3, as calcium is +2 and carbonate is -2. Going to react with hydrochloric acid, which is HCl. This is a double displacement reaction, positive, negative guy, positive, negative. So we're going to switch partners here, basically. So that's going to give us a little calcium chloride, which should be CaCl2. And it will give us really some carbonic acid. And it's actually this carbonic acid that will break apart into H2O and CO2. That is where our CO2 actually comes from, is it goes through a decomposition reaction and will break apart. Question on that there. We do need a balance, so I think we need a 2 here. And I think at that point we should be good, I believe, if I'm not mistaken. So we should be good. We got CO3, CO3. Got 2 of those, 2 of those, 2 of those, 2 of those. All right, so I'm going to just kind of put my water and CO2 up on top so we can kind of see it. But again, that is where it comes from there. So we'll go up here and put our water and our CO2 here. All right, so now that we have the balanced equation, we are interested in the volume here of this, obviously at 745 and also 23 degrees Celsius. In this case, though, we are starting with grams of our calcium carbonate, which is 35.3. And also 21.9 grams of HCl. So this is a stoichiometry problem. Is this a limiting reagent problem? It is, because we have grams of both reactants, which means we definitely could get to moles of both reactants. So we do have to, in this one, actually add that step in where we figure out the limiting reagent. So first step is still the same. Second step, we're going to convert to moles. So I'm going to take 35.3 grams of CaCO3. I'm going to go to the periodic table and use the molar mass there and try to add it up right. So 4008 plus 12.01 plus 3 times 16 looks like 100.1 grams per mole of CaCO3. And that would get me 35.3 divided. It'll give me something like 0.3527 moles of CaCO3. We'll do the same thing for our other reactant, which is the HCl, 21.9 grams of HCl. Once again, go into the periodic table, 1 hydrogen at 1.008 and 1 chlorine at 3545 gives us 36.46 grams per mole of HCl. And that's going to get us, looks like 0.6007 moles of HCl. Remember, as we did before, this is really your starting amount of each of these. Remember, one way that you can figure out which one is the limiting reagent is you're going to pick one of them and try to figure out how much of the other one you need to use it all up. So in this case, I want to know how much HCl is needed in this case to use up my calcium chloride. So I'm going to take the moles of my calcium chloride. I'm going to do a mole to mole relationship between the two reactants from the equation. So that is a 1 to 2 relationship. So in this case, 1 mole of calcium carbonate will give me 2 moles of HCl. And that will tell me that I need, in this case, 0.7054 moles of HCl is needed. Again, you want to compare that to the moles that you are starting with. And in this particular case, do I have enough? I do not, right? That means that the HCl in this case is our limiting reagent, and this guy would be our excess reagent. Any questions on that part of it there? Once we did that, remember you always want to start with the starting amount of your limiting reagent. So you want to come back to the starting amount here, and we will go 0.6007 moles of HCl. You now can do your mole to mole relationship between the limiting reagent, which is the HCl, and your product here, and that is a 2-to-1 relationship. And that would give me 2 moles of HCl, 1 mole of CO2. And I can take that basically and divide it by 2. Going to give us 0.30035 moles of CO2. I now have my moles of CO2 to go with my pressure and temperature. Now I can use the ideal gas law here to solve for what I'm looking for. And we do need to do some conversions here. So maybe I'll just get rid of some of this stuff up here that we don't even need anymore, I don't think. Get rid of all that there. It'd be easier to see if I go higher up, I think. So obviously here we need to convert our temperature into Kelvin. So we got to add a 273.15. That's going to get us 273.15 plus 23, 296.15. Our pressure is also not in the correct units. We need to convert it to atmospheres. So we'll go 745 millimeters of mercury divided by that 760 number to convert it into an atmosphere. That'll give us 745 divided by 760. We'll go 0.9803 atmospheres. Now we have everything that we need. So we could go into our ideal gas law here. Our PV equals nRT, solving for V, nRT divided by V. And do it on the next page so it'll be easier to see. So V is equal to nRT divided by P. So our moles was 0.30035. Our R's are constant. Our temperature that we converted to, we're at 296.15. All divided by our pressure, which was 0.9803. Again, atmospheres are going to cancel. Kelvin cancels. Moles cancel, leaving us liters. That gets us here. A volume of 7.45 liters of CO2 was produced in this case. That would be a theoretical yield in this case, right? Based on the limiting reagents. Any questions on those steps there? So again, as you hopefully see, stoichiometry, really the same steps. The only difference is somewhere along the way, usually you need to use an ideal gas law or a gas law. Again, if you use the gas law early on in stoichiometry, you most likely would be solving for moles. If you use it towards the end, like we just did there, you would probably be solving for volume or something like that. Any questions on that there? All right. All right. Why don't we take like a 15-minute break or something? Stretch our legs, come. Okay, we're going to continue on here. First off, any questions on anything we've been talking about, stoichiometry or any of that type of stuff? Okay, Then the next thing we're going to talk about is Dalton's law of partial pressures. And it does sound kind of difficult, but it's actually a fairly straightforward idea here. And what happens is a lot of times when we do have gases, they do come as a mixture of gases. So a lot of times we don't just have one gas sort of in there or in the container by itself. So when we do have mixtures of gases, for example, if we had a container here that had just gas molecule A in there, the total pressure of this container basically is basically all a result of the pressure associated with that one gas molecule or that A gas molecule that's in there. Now, when we have a mixture of gases together, say we have gas molecule A, a different gas molecule, C, or however many we have. The result of that is each of the gases are basically contributing to pressure of the system. And the total pressure here would be a result of the pressure of A plus the pressure of B plus the pressure of C. Now, each of these are partially contributing to the overall pressure of the container, and that is why they are referred to as partial pressures, because they each contribute to the overall total pressure. The total pressure is really the atmospheric pressure. It is, for example, when you took a barometer reading and the experiment we did, that barometer reading is the atmospheric pressure, and that is the total pressure that you have. Now, how do we get all these sort of gases, pressures? Probably the most common way that we could get the pressure of each of these gases is to frankly just use the ideal gas law. PV equals nRT, solve for P, nRT divided by V. We basically would do the ideal gas law for each gas individually. And this goes back to what we talked about earlier, that an ideal gas, right? An ideal gas, basically one of the things that makes something an ideal gas is the idea that even if there are other gas molecules in the same container with it, there really is no interaction between the different gas molecules, which means that even though they're all flying around together, A, B, and C in this example, we could almost look at each gas as being in there by themselves, like A's in there by itself, B's in there by itself, and C's in there by itself. Again, because in an ideal situation, there's no real interaction between all of the gases. The other nice thing about this is because all three of those gases are actually in the same container, when you do the volume, that's for everybody. So the volume will be the same for everybody. The temperature will also be the same for everybody. So usually the volume and the temperature is the same for all the gases because they're in the same container. That means if you look at the ideal gas law, the temperature and volume is the same. R is a constant. Really, the only thing that will probably change for each gas is how many moles of it that you have. And then basically, like I said, all you have to do is go in and do the ideal gas law separately for each gas, and then just add up all the pressures together, and you'll give you your total pressure in this case. And that's what we see here. Again, gas A, which is red, and our gas 2, which is green. When we put them together, we just basically have to add up our total pressures. And again, that is the commonest way to sort of do it, unless you are given, for example, a partial pressure and a total pressure. Then you could just basically subtract and get the other partial pressure that's present. And again, that is still the ideal gas law, so same rules apply. Everybody needs to be in the right units when you go into there to make sure everything cancels out correctly. So why don't you give it a go? Say you have 5 grams of helium is added to 5 grams of neon in a 2.5 liter container at 27 degrees. We're looking for the partial pressures of each gas and also what is the total pressure. Helium is 4.003. And neon 2018, I believe. So we're looking for three things in this problem: two partial pressures and a total pressure. Okay, so let's take a look. So in this case, that's nothing. There it is. So in this case, we have basically a container that has both of these gases in it, and we want to find the partial pressures of each. So really, we're going to use our ideal gas law and solve for P. We're just going to basically do it twice, one for each gas. So again, the idea here is, even though they're in there together in an ideal situation, it really doesn't matter. You could think that they're in there by themselves. So a couple things that we need to obviously, like normal, convert our temperature into Kelvin. So that's going to get us there. Our 2 something or 300 here. Our 300.15, 300.15 Kelvin. Our volume's in liters, so we're good to go. That is going to be the volume and temperature for each gas. R we always have, which is our gas constant, 0.08206 liters, atmosphere, Kelvin, mole. So we do need to get the moles of each of them. So we'll go 5 grams of helium. We'll use the molar mass of helium, 4.003 grams per mole. That's going to get us here 5 divided by 4.003, 1.249 moles of helium. We'll go 5 grams of neon, do the same thing. 2018 grams per mole of neon. Going to get us here 0.2478 moles of neon. That now is everything that we need. So we'll solve for helium first, which is nRT divided by V. So putting in our moles of helium, 1.249 moles, our gas constant, and our temperature, which is not that, but let's put the right temperature in. We got 300.15 Kelvin, all divided by 2.5 liters. Liters will cancel, Kelvin will cancel, moles will cancel. Going to leave us atmospheres here. And for our helium, that will get us looks like 12.3 atmospheres. That number would be the partial pressure of helium in this case. We're going to basically do the exact same calculation for our other gas. The only difference going to be our moles. So we want to use our moles for the other gas, 0.2478. Our R, 0.08206. And our temperature, 300.15. Divided by 2.50 liters. And that's going to get us here. That's going to get us here 2.44 atmospheres. That is our partial pressure of neon in this case. First off, any questions on the calculation up to there? So now that we have the two partial pressures of the gases in this mixture, to get the total pressure, all we have to do is add them together. Yes. So we're going to take the partial pressure of helium plus the partial pressure of neon. So that's going to be 12.3 atmospheres plus 2.44 atmospheres. Going to get us here 14.7 atmospheres as our total pressure in this case. Any questions on that one there? By the way, which one is contributing most of the pressure in this case? Is the helium, way more pressure. Any ideas why that is? It's because helium is lighter, yeah? Helium is much lighter than neon, which means because it's lighter, it actually has a higher velocity. It's flying around a lot faster, causing more collisions and contributing more to the pressure than the heavier, slower moving neon in this case. Any questions on that one there? All right, let's skip that, I think. Let's see here. That's what we just did, I think. Let's talk about another type of partial pressure situation that can occur. And that is one that we don't do this lab anymore. We used to do this lab. But for example, if you took some potassium chlorate here and you put it in a test tube, which you used to do, and you heated it up, it would go through a decomposition reaction and produce some KCl and some oxygen gas in this case. And you go through a nice decomposition reaction, probably some balancing needed here, maybe like a 2, and a 3, maybe. And in this particular case, what would happen is you would heat this up and basically it would start to decompose and produce some oxygen. That oxygen has nowhere to go but through the tube into this receiving jar. This receiving jar, kind of like your tube you used last week that was full of water. Once the gas comes in, what will happen is the water will exit basically the jar. And you will be left with, much like you had in your tube, this sort of empty area of your tube or your jar. And this empty area is really not empty. In this case, for example, this is where you would find your oxygen gas being present. That's where you collected it. Now, whenever you sort of collect a gas like you did last week, and in this type of experiment where water's involved, because the reaction will heat up usually and provide some type of energy, usually when you heat up water, you also will collect with it some water vapor. So you'll collect some water vapor with it. So you actually end up getting a mixture of two gases, one you're really not interested in, which is the water, and one that you are interested in, which in this example is the oxygen. In the example of the experiment you did, you were interested in the hydrogen gas, not really the water that came with it. That is why, if you remember, you had to go to that chart over there, right, and find the vapor pressure of water at a particular temperature. So in this situation, our total pressure will actually equal the pressure of the gas you're interested in plus the vapor pressure of water. The vapor pressure of water is, much like you did last week, a value that you could find on a table. In your book, there'll be a table as well of some vapor pressure of water at different temperatures, and you'll look it up. So usually when we do an experiment like this, like I said, the water is really not part of what we're interested in. It's really just a byproduct of how you collected the gas. You got a little extra water for free. So if you want to figure out the pressure of your gas you're collecting, you would take the total pressure and minus the vapor pressure of water from it. It's sort of a correction value. It is also why sometimes in labs they refer to that as the pressure of the dry gas, like you subtracted off the water's contribution to it, and you dried it out basically. So we're interested in just the pressure of the gas that's there. Any questions on that there? So that's a very common sort of partial pressure situation that occurs. How do you know you have that situation in a book problem? Usually there's some words that are usually used, something like you collected the gas over water is usually key, that's some type of problem that's happening here that you need to subtract off the water vapor pressure. Or it will sometimes say it is saturated with water vapor. So if you come across a problem where it says you collected the gas over water, or it's saturated with water vapor, those are all keywords that you probably need to go find the vapor pressure of water and subtract it to get the proper pressure that you need. And here is a table from your book of that. And again, much like the table that's up there on the board, you look it up based on temperature. You can find the vapor pressure of water. You do want to make sure unit-wise everybody's agreeing. So your pressure from the barometer or your total pressure and the vapor pressure, you do want to make sure that they are in the same units. So why don't you try one here? A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753. What is the partial pressure of oxygen if the vapor pressure at 30 is 31.824? Saturated with water vapor. That again tells you basically you collected that gas over water and you do need to kind of correct for it. So again, the total pressure here would be the pressure, in this case of oxygen, plus our vapor pressure of water. This is the value of the vapor pressure of water at 30 degrees Celsius. Again, if it wasn't given to you, you would need to reference a chart like this that you have, or table that you have in your book to find it. And then we can actually just solve here. So we know the total pressure is 753 torr equals the pressure of oxygen plus the vapor pressure of water, 31.824 torr. Basically, it's going to subtract it to the other side. And that's going to give me a partial pressure of oxygen of 721 points. Oh no, I guess we'll go 721. Seems good. Torr. We want it in atmospheres, so we will divide by 760 here to convert it into atmospheres. And that's going to get us here 0.949 atmospheres as the dry pressure of the oxygen gas in this case. Any questions on that there? So most common way, probably partial pressure and ideal gas law, just separately for everybody. This is also a very common way as well. Again, if you're just given a partial pressure, like I said earlier, and a total pressure, all you have to do is maybe subtract to get the other partial pressure. They should all add up to the total pressures as well. Any question on partial pressures? All right, so some of the parts of the kinetic molecular theory we sort of covered as we went through this chapter, but here are the sort of main aspects of it. Gases, as we talked about, consist of tiny particles. They could be atoms or molecules. The particles are small compared to the distances between them. So as we talked about, one of the things that makes something an ideal gas is number 2 there. The volume of the individual gas molecules are assumed to be negligible or 0. And again, that is basically one of the things there that makes something an ideal gas. The particles are in constant random motion, colliding with the walls of the container. Those collisions, again, is what causes the pressure that we exert on, or the gas exerts. Again, the higher the number of collisions, the higher the pressure we will have. And number 4 there, again, is the second thing that makes something really an ideal gas, is the idea that particles will not attract one another or repel one another if they're in the same container. So even though we got a lot of gas molecules flying around, there's basically going to be sort of no interaction really between the different gas molecules. That again is what allows us to do the calculation like we just did a second ago, to do like the partial pressure calculation with each gas separately, even though they're in the same container. Because there's no interaction between them, it won't affect anything. As I mentioned earlier, if there was interaction between gas molecules, for example, you have this gas molecule heading towards this wall, but maybe it's attracted to this gas molecule, it would actually slow it down and could affect the pressure that you would see in that situation. Or if it was repelled by that gas molecule, it could sort of propel the gas molecule into the wall faster than it normally would as well. So under ideal conditions, we don't have to worry about that sort of interaction between different gas molecules. We could assume nobody's basically interacting with each other, and it makes things a lot easier. The average kinetic energy of a gas particle is directly proportional to the temperature in Kelvin. And again, as the temperature increases, we do expect the gas molecules to have more energy. to start to fly around a lot faster. And that means at high temperatures, we get fast moving gas molecules, more collisions probably with the container, unless the volume moves. Low temperatures, we're going to have less collisions happening. They're moving around a little bit less as fast, not as fast. The pressure and temperature, as we talked about with Guy Lucix, if we have that rigid container where the volume will not adjust, again, we would see an increase in the pressure as the temperature goes up because of the increase in collisions, and we would see the pressure start to drop in a case where obviously we lowered the temperature because of the less collisions that's happening. Volume and temperature, remember that's Charles' law, and that is how it is able to keep it at constant pressure is the volume will adjust. And again, as the temperature increases, the volume gets larger, it allows everybody more room to fly around in, keeps the number of collisions relatively constant and the pressure constant, and vice versa. If you lower the temperature, everybody's flying around slower,